Hello, everyone. Welcome back to the next part of our Introduction to Intelligent Systems. So in this next part, I'm going to talk about one of the main topics of our course, which is knowledge graphs. So here we address an additional problem in terms of managing knowledge in an organization or in a company that goes beyond just the information in the documents. The underlying problem is known as the information silo problem. Like a physical silo, in many organizations and companies, you also have information silos, meaning you have different databases, different systems holding different sources of knowledge. For example, in a software company, you have knowledge stored in emails. You might have lots of documents on the cloud or an internal document server. Then you have something like a development server with source code and issue tracking. You have information about design, information about customers. So all of these typically have their own system and their own database. And they come in very different formats. Now, some are text documents, some are spreadsheets, some are emails, some are in the source code repository, commit messages, things like this. So now if you want to support this with some kind of automated tool, you have the additional problem that all of this knowledge is disconnected. And there is a lot of value in bringing these separate information sources together, because then you can make conclusions across multiple sources. So that's the problem of knowledge integration. Now, specifically, we want to be able to connect different information silos together and then build what's commonly known as a knowledge base. Once we do this, meaning we are able to bridge these different technologies with a common format, then we have the additional benefit that we could also include external knowledge sources. You'll see that there are a lot of these knowledge bases available online on the web in an open format. And then you can use these to get further information and enrich your internal documents. For example, let's say you have some internal documents that talk about design or talk about experience that one of the staff members has in designing developing systems. And in there, it mentions a technology called a support vector machine. By itself, this is just a string of 3 words, but if you connect this with a knowledge source, like the one shown here, Wikidata, then you can find a lot more information about this. This is a kind of supervised statistical learning. So this is an algorithm, which is a subclass of supervised learning. And if you look later, you'll see this is a kind of machine learning algorithm. So now we are not just able to connect knowledge internally with each other, you can also connect it with external knowledge sources. And then from there, get even more information and do more reasoning about the data that you have. So this brings us to version 3 of our architecture. We still have our knowledge worker dealing with a lot of documents. We talked about how NLP pipelines, text mining can help you to automatically analyze, filter, and extract information. But now the new thing is that we store these information in a structured format, in a so-called knowledge base. So we're using we'll see later, a so-called knowledge graph to store this information. And then we can not just incorporate the information from documents and other sources that we have, we can also use information from external knowledge resources. There is something called the linked open data cloud. We'll have a lecture on that in a couple of weeks. So you can use all of this information in your application as well. So let's talk about knowledge graphs. Knowledge graphs are about representing knowledge in form of a graph. And graph here means a graph in the mathematical sense. So something with nodes and edges connecting the nodes with each other. So in this case, you can see it is a directed graph. And what makes this a knowledge graph is that we represent knowledge about some domain in graph form. For example, here is a person, Bob, and we represent Bob as a node in this graph. And then we can connect other nodes using edges in this graph. For example, here is another node, which is about the painting, the Mona Lisa. So now we can represent the knowledge that the person Bob is interested in the Mona Lisa by creating a directed edge of type is interested in. So you can see where this is going. Now we have a graph with lots of information about here, people, paintings, and something like the creator, the painter, Leonardo da Vinci is another node in the graph. So we can model that the Mona Lisa was created by Leonardo da Vinci. We can have a movie about this painting. So again, we can have a movie node. Here, this represents a movie, and this is about the Mona Lisa. And we can model further information about Bob, that Bob is a person and not an AI, that Bob is a friend of another person called Alice. And then, of course, you can have a lot more information coming out from Alice. Now, Leonardo da Vinci has other paintings, Alice has other friends, and so on and so on. So that's the core idea of a knowledge graph. Knowledge graphs have a long history in artificial intelligence. They go back to some early techniques in AI, but they really became the graphs that we're looking at now. They became part of the World Wide Web technology called the semantic web. So essentially, this is a technique to incorporate data on top of the World Wide Web that is meant for humans. So here, you are all familiar with the old-fashioned web, just standard websites. This was extended into the social web. So we have all of these social websites that connect people with each other. And the technology that you are probably not as well familiar with is this semantic web, which comes out of research that started in the late 1990s. And over the last 10 years has become widely adopted in commercial settings. So this is itself a sub-branch of artificial intelligence, and this is one of the major topics that we'll look at in this course. And nowadays, we are sort of in the area where these different technologies become merged with each other. For example, all of these modern chatbots that can understand natural language and answer questions about people and all kinds of questions that you ask, they are sort of the fusion of all of these previous technologies that came. So what makes this graph a web technology? The first picture that I showed you was a somewhat simplified version. And as we'll cover in more detail next week, the way it really looks is that all of these entities in here are URLs. So something like here, Bob is not just Bob, it's an actual URL. In this case, we're using an example URL, example.org, and there is Bob, the entity. Similarly, the Mona Lisa is not just the name. There is a URL that points to the Mona Lisa on the web in one of these knowledge bases. So this makes this technique a web technology. And just like web pages can be distributed all over the world, the knowledge that we have here about people, about creators, about content, about the relations can be distributed all over the world and linked to each other using web technologies. Once you start implementing this, you don't draw a graph because you cannot input a nice picture into a program. You'll see that this is done with various web standards. One that we'll start talking about in the second week is RDF, and this looks like here. So the details we'll cover next week, but you can roughly recognize how the different lines here match to the graph from the previous picture. For example, here we have Bob, the entity, and the Bob is a person, and Bob knows Alice. So this corresponds to the node here and the relationship that Bob knows Alice. So this is what you would actually input into a program to automatically work with this knowledge in there. And then the program, the AI, can go through this knowledge, link the entities, and answer questions about it. And this is something that has been incorporated, for example, in search engines. Yeah, you all know when you ask Google or some other search engines about an entity, like who was Steve Jobs, you don't just get web page results like you used to get from Google with pages containing information about Steve Jobs. Now, very often you get these info boxes here on the side. And then you get detailed information about this entity, in this case, the person Steve Jobs. And now if you look closely, you see information, some general description, but then you see something like relations between Steve Jobs was born on February, Steve Jobs died on a certain date, Steve Jobs had a spouse, Laureen Powell, and so on. And if you think back here, this is exactly based on a knowledge graph. So you have Steve Jobs has a spouse and then another person and so on. So this is also known as Google's knowledge graph. Again, we'll talk about this in more detail in the upcoming weeks, but this is just to show you that this is one of the applications of this knowledge graph technology. And a lot of this information is actually not just contained in the Google internal knowledge graphs. A lot of this information you can get from publicly accessible knowledge graphs. So there's one that we'll talk about in detail called DBpedia, and you'll see that the information you have in DBpedia is more or less identical for many entities that you get from these Google knowledge boxes. And there's some reason because Google incorporated a lot of this information as well. Obviously, Google has this greatly enhanced internal knowledge graph, but you'll see there is a lot of information that you can use directly in open access knowledge graphs. So you can build smart AI applications that can answer questions about many entities, like in this case, about Steve Jobs. One of the related problems and challenges when you want to use this and start out from natural language text is you have to make a connection between the text and an entry in a knowledge graph. This is somewhat related to what we talked about before in text mining. You wanted to find things like persons. For example, if you're looking for the person, if you have a text mentioning something like Paris, then this could link to Paris, the city, or Paris Hilton, the person. Likewise, in the example here, we have tree, and tree can link to either the tree as a botanical object or tree as the data structure. And it can be quite difficult, and it's quite challenging often to find the right entry in a knowledge graph based on natural language text. Now you can see that very often you need some context information to find the right entry. And very often this can go wrong. And again, this is an example of AI becoming entertaining when things go wrong. This is an example that was widely published some time ago, where somebody asks Siri, what is a group of moose? Now, is it a flock of moose or a clouder, or what do you call it? And the answer that came back from Siri was, surprisingly, it's Jared Padalecki, which does not make any sense, right? So what has happened here? Now, if you understand it, the technology behind it, there is again a knowledge graph. And when there is a question coming in, it has to map entities from the question onto the knowledge graph. And in this case, it got this wrong. I think Moose was some of the names of the roles this actor played in a TV series or something like this. And anyway, Siri got this wrong. It mapped it to the wrong entity, and it gave this entertaining answer. So one of the topics that will come to in a couple of weeks, once we understood all the technology behind knowledge graphs, how to build knowledge graphs, how to use them, is how to work with all of these existing knowledge graphs. And just like the web, there is also a huge web of accessible knowledge graphs. It's just called the Linked Open Data Cloud. And DBpedia that I just showed you is just one of these nodes in this knowledge graph. So now an additional challenge is this, this linking step. You have a text, for example. This could be a document in a company or an email with a question or something like this. And in there now you just want to recognize not just the entities, but additionally you want to link them to information in a knowledge base, in a knowledge graph. For example, here you could link smartphone to the device smartphone, which in turn then links to other information. Because it's a graph, once you have found an entity and linked it to a specific node in this knowledge graph, then now you can make connections to other pieces in the graph and get more information about them or connect them to other documents that you might have in your company or organization. So this is what enables AIs, intelligent systems, to do some kind of reasoning about the knowledge. So you can combine different pieces of information and conclude new information. You can reason about them and derive new knowledge that is not explicitly mentioned. Again, an example, Google is always experimenting with these techniques. So you don't always get the same result when you ask the same question. But one example here that worked quite reliably, if you ask a question like this: what was the US population when Bill Gates was born? So now you can see this is a bit more complicated when you want to answer this, because it has to connect multiple pieces of information. It has to find out that Bill Gates is a person, just like for Steve Jobs before. Then you have to find in that knowledge graph the date of birth. And then you go to another piece in the knowledge graph where you find information about the population in the US. And then you can answer the question. So in this case, it is not just returning just one node. In this case, it also brought up the info box about the United States, but the really interesting piece is that Google was able to reason. Now it was able to connect the entity Bill Gates in the knowledge graph, find out the birth date, and then connect the year of birth with the information in the knowledge base about the US population and give the right answer. So this is an example about reasoning, and you need first the knowledge graph with the information, and then you need on top the reasoning technology. Another example, don't try to find this web page. It's not there anymore for reasons that I'll explain in a minute. You can see this is an older screenshot I took and fortunately kept. So this was a system called True Knowledge. And similar to Google here, you could answer, it could answer questions that you type in a natural language. So here, for example, what time is it at Concordia University? And again, this is quite tricky because now it's not just about a static piece of information. This is not something you can look up in a web page. This is something that changes literally every second. So a system has to be able to do a somewhat complex chain of reasoning to give you the right answer. It has to find out that Concordia University is an entity that is located in a certain country. That country has a certain time zone, that a time zone of something is permanent and the time zone doesn't change, but the time inside the time zone changes. And here you can, the system was interesting because you could see the whole chain of reasoning. This goes on a lot further. So this is really a 100-step process of reasoning, and you could follow each step. And in the beginning, you could give feedback to the system and tell it, okay, you did the wrong reasoning or you had the wrong facts in your knowledge base. And then if everything worked out, in this case, it gave the correct answer for this chain of reasoning. So again, this website isn't there anymore. That was a startup in the UK, and they renamed themselves later on, but more importantly, the startup was bought up by Amazon, and this is now the reasoning engine that Amazon is using inside Alexa, the digital assistant that they have. So a major part of the course, the next 4 weeks roughly, will talk about these underlying technologies for building knowledge graphs and knowledge-based applications. These are based on standards that come from the W3C, the World Wide Web Consortium that also standardizes the web and HTML and so on. You're probably familiar with HTML, URIs, and XML. And here in this course, we are covering techniques like RDF and RDFS, which are important for these knowledge graphs. We cover a little bit of a technology called OWL for building ontologies. We're looking at how we can query these knowledge graphs using a query language called Sparkle. And then we look at how we can build applications on top of it, like chatbots, digital assistants. So this comes out of web technology, as I mentioned earlier. This was developed as part of a research that's called the semantic web. Nowadays, it's better known as knowledge graphs and related technique, primarily because Google called their implementation the Google Knowledge Graph. And since then, everybody is talking about knowledge graphs. Yeah, of course, Google did it. Everybody else also wants to have a knowledge graph. But the underlying technique that was developed since the late 1990s was research called the semantic web. So the core idea is that on top of the web that we have for humans, with web pages that you and I can read, we also have a web of data that machines, AIs can read. Because if you just have a web page with lots of text, that's nice for you to look at, but by itself, this is not very useful for a system. So we need some kind of formal language for representing this knowledge in form of a knowledge graph. This is called RDF, the Resource Description Framework. And we need a language to be able to query this graph. So this can look like something like here. If you have done databases, you know query language like SQL, and it actually looks somewhat similar. It has some similar ideas, but in databases and the Sparkle query language, you have, the SQL query language, you have tables. And the difference here is that what we are querying is a graph. But by itself, you'll see next week that this is a rather simple way of representing knowledge because everything is done in form of so-called triples. Triples of a subject, a predicate, and an object. For example, Bob knows Jane. Then we have subject Bob, predicate knows, object Jane. So this technology is now all over the web and used in all kinds of applications, social networks, Facebook, LinkedIn, knowledge representation like Google's knowledge graph, and is the underlying technology for many modern AI applications. The good thing is that there is a lot of data out there that you can directly use, and we'll talk about some of those in a couple of weeks. But just to show you some examples, there's information about social networks. There's a so-called friend of a friend ontology that models people and how they know other people. There's information about digital resources on the web. This is called Dublin Core. And this models information that you can find, for example, in archives, in libraries, but also in museums. If you want to exchange information, let's say for a museum, what kind of artifacts they are, who created them, where they are located, then it wouldn't really help if every museum in the world has a different catalog, a different database about their artifacts, about their exhibits. Then it would be very hard to find out paintings of the same artist. They are located in different museums around the world, you would like to have some kind of open representation. And the Dublin Core standard is one widely used standard for representing this information in digital libraries, in museums, in collections, and so on. Another example is the gene ontology that models knowledge about biological information, processes, and so on. So here it's interesting that this kind of technology was adapted very early on in biomedical research, because they very early on had the problem that they have too much data for humans to handle, especially with modern gene technologies. These experiments would create way too much data for a human to look at manually. So they started as one of the earliest adopters of these semantic knowledge graph representations. And one example is the gene ontology. Here's a very small part of this gene ontology, which describes biological processes, cellular processes, defense response of cells, response to stress, and so on. So essentially, if you would want to write an AI that understands something about biology, let's say you work in drug discovery, and you need information about biological organisms, cellular processes, and so on, then your AI could understand all of these concepts by loading the corresponding information, in this case, from the gene ontology. So this brings us to the end of the second part of the introduction. The core idea here that I showed you is the idea of a knowledge graph, what a knowledge graph is and what you can use it for example, for integrating different sources of knowledge in an organization. This gives you the means to have something like an AI to automatically analyze this information and, for example, derive new insights by combining the knowledge from multiple sources together. And not just combine knowledge internally between the documents and databases inside a company or organization. You can also go outside to these knowledge bases on the web and further enrich the information. So here we are going to learn about the technology. First, the theory, how you build these knowledge graphs, and then in the labs, you learn how to write programs using these graphs, work with so-called triple stores, query engines, and so on. Again, this is something that has matured a lot over the last 20 years. There are both open source libraries and commercial platform providers for these. So this is something that's nowadays quite robust and widely available. All right, that was the second part. And in the next video, I'll talk about the last part of the introduction, intelligent agents. See you then.